Imagine a silence so deep it feels heavy, broken only by the sound of something massive shifting through dark, ancient water. 60 million years ago, in a world recovering from ash and fire, the humid rainforests of Colombia birthed a creature that defies our modern understanding. This is the realm of the Titanoboa. But this story is about more than just size. It is a grand mystery wrapped in the fossilized coils of history. Why do we feel pulled to uncover the secrets of this 40-foot phantom? Because understanding this giant offers us a rare window into a feverish chapter of Earth's past. It challenges what we believe nature is capable of creating and reminds us that our planet has nurtured life forms far stranger than fiction. You are invited to step back into this lost epoch with me. We will look beyond the fear of the predator to find the beauty of the science, exploring how heat and time crafted the ultimate survivor. Settle in, let your curiosity take the lead, and let us gently wade into the past to meet the true lord of the rainforest. Let's begin. There is darkness, complete, total darkness. And in that darkness, if you listen very carefully, there is a sound. It is deep and slow, and it does not quite sound like anything you have heard before. It sounds like something enormous breathing, something patient, something that has all the time in the world. Hold on to that sound for just a moment. Now picture a coal mine in northern Colombia. Picture the heat of a tropical afternoon, the dust hanging in the air, the sound of heavy machinery cutting through ancient earth. Workers moving through layers of rock that have not seen daylight in tens of millions of years. This is the Cerrejón mine, one of the largest open-pit coal mines on the face of the earth. And on most days, what comes out of that ground is exactly what you would expect: coal, dark, ancient, compressed plant matter from a world long gone. But one day, something else came up, a piece of rock that was not quite a rock. A curved, dense, unusually large fragment of fossilized bone, and when the right scientist finally looked at it under proper light, in a proper laboratory, with all the tools of modern paleontology at hand, the room went very quiet. It was a vertebra, a single spine bone from a snake, and it was the size of a grown man's closed fist. Now, if you know anything about snakes, you know that snake vertebrae are not large things. The biggest snakes alive on Earth today have vertebrae roughly the size of a large grape, maybe a golf ball at the most extreme end, not the size of a fist, not even close. What had been found in that Colombian coal mine was a bone from a snake that should not have been possible. A snake that rewrote the rules of what this planet has been capable of producing. A snake that was 13 meters long, that weighed more than a ton, and that had been resting quietly in the ground for 60 million years, waiting to be found. 60 million years. Think about that number for just a moment. The dinosaurs were already gone by then. The ancestors of horses were tiny creatures no bigger than a house cat. The creatures that would eventually become human beings were still tens of millions of years away from existing in any recognizable form. And in the warm, dark rivers of an ancient tropical world, this snake was already the undisputed master of everything it touched. Its name is Titanoboa carajonensis, the Titanic boa from Cerrejón, and this is its story. But here is what makes this story different from every other story about a big prehistoric animal. This is not just a story about something large and frightening that used to exist. This is a story about the world that made it, about the forces of heat and time and geography that allowed something this extraordinary to come into being. It is a story about how one remarkable discovery in a coal mine changed the way scientists understand ancient climate. It is a story about what happens when the world changes, and even the most perfectly designed creature cannot change fast enough to keep up. And in a quiet, steady, deeply important way, it is a story about our world today, about where we are headed, and what the bones of a 60-million-year-old snake can tell us about the future we are building. So stay with this. because by the time this is finished, you will see the world differently. You will look at a river and think about what might live in it. You will feel the heat of a summer afternoon and understand it in a way you never have before, and you will carry with you, for the rest of your life, the image of something impossibly large and impossibly ancient, moving through warm, dark water in a world that no longer exists. The greatest snake that ever lived is waiting to tell you its story. Let us begin. Chapter 1. The Find. It starts, as most great discoveries do, not with a dramatic moment of revelation, but with a very ordinary day that quietly becomes something else entirely. The year was 2002. The place was the Cerrejón coal formation in the La Guajira region of northern Colombia, not far from the Caribbean coast. This is a part of the world that most Americans have never visited, a landscape of tropical heat and dry wind and enormous open pits where machines the size of buildings dig through millions of years of accumulated earth. Cerrejón is one of the most productive coal deposits in the Western Hemisphere. Workers there are accustomed to finding things in the rock. Fossils are not uncommon in coal country. Ancient plant impressions, petrified wood, the occasional old bone, these things appear, get noted or ignored, and the work goes on. But on one particular day, in that particular year, a geology student named Fabiani Herrera was working at the site as part of his studies. He was doing what geology students do, walking the cuts, examining the exposed rock faces, taking notes. And he noticed something in a chunk of stone that had recently been brought up from a lower layer. It was a curved fragment, dense, dark, with a particular texture that rock simply does not have. He picked it up and turned it over in his hands. He knew immediately it was biological in origin. He knew it was bone. What he did not know, what nobody in that mine knew that afternoon, was what kind of bone it was, or what kind of creature it had come from. He took it with him. He labeled it carefully, and eventually it made its way to a drawer in a university storage facility, where it sat quietly, as fossils sometimes do, waiting for the right set of eyes. Those eyes belonged to Jonathan Block. Jonathan Block is a vertebrate paleontologist at the Florida Museum of Natural History at the University of Florida in Gainesville. He is the kind of scientist who has spent his entire career thinking about ancient bones with genuine love and curiosity, thinking about what they meant, what they reveal, what story they are trying to tell. When Block first encountered photographs of that Cerrejón vertebra, he had a reaction that scientists do not often describe publicly, because science is supposed to be measured and precise and resistant to drama. But Block has said that his initial response to seeing that bone was something close to disbelief. Not because it was unclear what it was very clear what it was. It was a snake vertebra. The shape, the structure, the distinctive ball and socket joint system that snakes use to give their spines extraordinary flexibility, all of it was unmistakable. The problem was the size. The bone was simply too large to be a snake vertebra. It fell outside the range of anything known, and in paleontology, when something falls outside the range of anything known, you have two choices. You can assume there is a mistake somewhere, or you can follow the evidence and see where it leads. Block followed the evidence. He got in touch with Carlos Jaramillo, a paleoecologist at the Smithsonian Tropical Research Institute, who had been working in the Cerrejón formation for years and understood the site better than almost anyone. Together, they organized what would become one of the most significant paleontological expeditions in the history of South American science. The expeditions took place between 2007 and 2009, and they were not glamorous operations. They were hot, exhausting, logistically complicated efforts, carried out in a working industrial mine, where fossil hunting had to be coordinated with the daily operation of enormous machines and hundreds of workers. The Sarajan mine management was extraordinarily cooperative. They understood what might be buried in their ground, and they wanted to know too. What came up over those 2 years of careful, patient excavation was staggering. Not one fossil, not 10. More than 180 individual fossil fragments, all belonging to giant snakes. Vertebrae of different sizes suggesting multiple individuals. Rib fragments, partial jaw elements. All of it fossilized to the dark reddish-brown color that ancient bone takes on when it has been compressed in rock for millions of years. Now, one important thing to understand about fossil snake skeletons is that they almost never come out of the ground in one piece. A snake skeleton is made up of hundreds of individual bones, many of them small and fragile, connected to each other in life by soft tissue that disappears long before fossilization is complete. What you find in the field is always fragments, pieces of a puzzle that you have to assemble using science, mathematics, and close comparison to living relatives. And that is exactly what Bloch and Jaramillo and their team began to do. They brought the fossils back to the laboratory. They cleaned them. They measured them. They photographed them from every angle. They compared them to modern boa constrictors and anacondas and every other large-bodied snake they could access. And they ran the numbers. The numbers came back extraordinary. This was not just a large snake. This was the largest snake the scientific community had ever documented from fossil evidence, by a significant margin. It was larger than the African fossil snake Gigantophis garstini, which had previously held the record. It was larger than any living species by a factor that made the comparison almost absurd. Then came the naming. In science, when you discover a new species, you have the privilege and responsibility of giving it a formal name according to the rules of biological nomenclature. The genus name must reflect something meaningful about the animal's character or nature. The species name typically honors the place of discovery or the people involved. They called it Titanoboa cerrejonensis. Titanoboa. Titanic boa. The name carries its own weight, does it not? There is something almost poetic about it. Scientists are not usually known for their poetry, but every so often a discovery is so remarkable that the name writes itself. The cerrejonensis part honors the mine, the Cerrejon Formation, the place where this animal slept in the rock for 60 million years and finally gave up its secret to a group of persistent, passionate, sweat-drenched scientists who refused to look away. In 2009, the formal scientific description of Titanoboa cerrejonensis was published in Nature, one of the most respected and widely read scientific journals in the world. Nature does not publish just anything. The bar for inclusion is extraordinarily high. A paper in Nature means the scientific community has looked at your work, checked it from every angle, challenged your methods and your conclusions, and come to the agreement that what you have found is real, significant, and important. The reaction to the Titanoboa paper was immediate and global. Scientists who had spent their careers studying snake evolution found themselves rereading the paper multiple times, not because it was confusing, but because they needed to sit with the implications. Paleoclimatologists, scientists who study ancient climates, paid particularly close attention because buried in the size of this animal was a clue about ancient temperatures that they had not expected and desperately wanted. Science writers and journalists began reaching out within hours of publication. And somewhere in the background of all that noise and excitement, deep in the Sarajan mine, the ground continued to give up its secrets, one fragment at a time. The story of Titanoboa had begun, but to truly understand it, to feel it in the way it deserves to be felt, you cannot start with the animal. You have to start with the world, because the world that produced this snake was as extraordinary as the snake itself. It was a world so different from ours that standing in it would feel like standing on another planet, and understanding it is the key to understanding everything that follows. Chapter 2. The Broken World. Close your eyes for a moment and try to imagine the world as it was 60 million years ago. Not the world of the dinosaurs. That era ended roughly 66 million years ago when an asteroid the size of a small city struck the Earth near what is now the Yucatan Peninsula in Mexico and set in motion a chain of catastrophic events that eventually ended the reign of the non-avian dinosaurs. By the time Titanoboa appeared on the scene, the dinosaurs had been gone for about 6 million years. That sounds like a long time, and in one sense it is. But in the scale of geological time, 6 million years is a relatively short window. Long enough for ecosystems to begin rebuilding themselves, but not long enough for them to have fully recovered their complexity and balance. This was the Paleocene epoch, a time scientists sometimes describe as a world that was healing. But healing from what and into what was not yet clear. Think about it this way. Imagine a forest after a very large fire. The fire is out. The immediate destruction is over. But the landscape is different now. The old trees that dominated everything are gone. There is light reaching the ground that never reached it before. And into that open, uncertain space, 1,000 different things are scrambling to establish themselves. Some will succeed, most will not. The forest will eventually grow back, but it will not be the same forest. It will be a new forest, shaped by different forces and different survivors. That is what the Paleocene was, a new world, growing up in the space left by the collapse of the old one. And the new world was hot. When scientists say the Paleocene was hot, they do not mean it was a little warmer than today. They mean it was dramatically, almost incomprehensibly warmer by the standards of the world we live in now. Global average temperatures were somewhere between 6 and 10 degrees Celsius higher than our current averages. That may not sound like much when you put it in those terms, but consider what it meant in practice. There were no polar ice caps, not a permanent one anyway. The Arctic had trees, actual forests of temperate and subtropical plants growing in the far north, in places where today there is only permafrost and ice. The ocean floors were warm. The deep ocean, that vast, cold, dark region that today acts as a kind of thermostat for the global climate, was significantly warmer than it is now. The entire planet was, in the truest sense of the phrase, a greenhouse. And at the center of that greenhouse, at the geographic heart of what would one day become South America, there was a landscape so different from anything that exists today that it requires a real effort of imagination to picture it. What is now northern Colombia, the same region where Cerrejón sits today, was not mountains. It was not the foothills of the Andes. The Andes did not yet exist in any meaningful sense. They were just beginning the extraordinary slow-motion collision of tectonic plates that would eventually push them skyward over tens of millions of years. At the time of Titanoboa, they were barely bumps on the horizon if they existed at all from most perspectives. Instead, what occupied that part of the world was a vast, flat, low-lying tropical swamp. Picture an enormous river basin, wider and longer than anything alive today, crisscrossed by warm, slow-moving rivers and shallow lakes and wetlands so extensive that the line between water and land was not always clear. The humidity was extraordinary. The heat was constant, day after day, season after season, without the relief of a cool autumn or a cold winter. This was a world without seasons as we know them, just warmth and more warmth, and plants growing in every direction as fast as living tissue can grow. Now, the reason this geography matters so much is that it was the direct cause of everything extraordinary about Titanoboa. Not just its size, though we will come to that. It was the cause of the food, the prey, the rivers full of enormous animals, the dense, productive jungle that fed everything below the apex of the food chain. Every extraordinary feature of Titanoboa traces back ultimately to this hot, flat, wet, impossibly productive landscape. Let us talk for a moment about what else lived here, because Titanoboa did not live in an empty world. It lived in a world that was, in its own strange way, as rich and complex as any ecosystem that has ever existed on this planet. The fossil deposits at Sarajevo have given scientists what they describe as one of the most complete pictures of a Paleocene tropical ecosystem ever found anywhere in the world. And what that picture shows is remarkable. There were fish. Not ordinary fish, mind you. Giant lungfish. Ancient and primitive relatives of the kind still found today in parts of Africa and Australia, but larger. Large bony fish that rivaled in size the biggest freshwater species alive today. The rivers were teeming with fish in sizes that modern anglers would find difficult to believe. There were turtles, not ordinary turtles either. Among the fossils found at Sarajevo alongside Titanoboa is a turtle called Carbonemys cofrini, whose shell was roughly 1.5 meters long. This was a turtle the size of a dining room table, massive, slow, heavily armored, and sharing the same warm rivers with the snake. We will talk much more about this creature later. There were crocodilians, ancient primitive relatives of modern crocodiles, though different in important ways. Slimmer in build, more adapted to chasing fish in open water than the ambush-hunting crocodiles of today. Several different species have been found in the Sarajevo Formation, ranging in size from quite modest to several meters in length. Not as large as the biggest crocodilians of today, but formidable in their own right. Formidable to everything, that is, except Titanoboa. And there were early mammals. This is perhaps the most surprising thing about the Paleocene to people who first learn about it. Mammals existed. They had survived the mass extinction that ended the Cretaceous. But they were small, modest. They skittered through the undergrowth, climbed in low branches, hunted insects, ate seeds and fruit. They were not players in the large animal drama of the Sarajevo rivers. Not yet. They were, in every meaningful sense, biding their time. The plants of this world deserve particular attention, because they were the foundation of everything. The Paleocene tropics were extraordinarily productive. The combination of intense heat, abundant moisture, and long days throughout the year meant that plants grew without the seasonal interruptions that limit growth in most of the world today. Enormous palms with fronds wider than a man is tall. Early flowering plants in extraordinary variety. Giant ferns carpeting the forest floor. Tall canopy trees draped with vines and mosses, creating a green ceiling so dense that the forest floor was in permanent deep shadow. The rivers themselves were choked with aquatic vegetation along their banks and in their shallow margins. The water was warm, murky with suspended sediment and plant matter, and rich with nutrients that fed the fish and turtles and crocodilians in extraordinary abundance. And moving through all of this, through the murky water and the dense riverbank vegetation, through the warm, shallow crossings and the deep, slow pools, was Titanoboa. It is important to pause here and let the setting settle. Because when you understand this world, the size of the snake stops being a mystery. It starts being the only logical outcome. A world this warm, this wet, this productive, was a world that was almost designed to produce an animal like Titanoboa. Not literally designed, of course. Nature does not design things. Nature runs endless experiments and keeps the ones that work. But in the Paleocene tropics of northern South America, every factor was aligned in the same direction, and that direction was toward something very, very large. In the next part of our journey, we are going to talk about just how large. We are going to talk about the science of measurement, the mathematics of bone and body proportion, and the elegant logical chain that allowed scientists to calculate the size of an animal from a single fragment of stone. And what they calculated will take your breath away. Chapter 3. How big was it really? Let us start with a question that seems simple but turns out to be deeply interesting. How do you measure something you have never seen whole? This is not a hypothetical problem. It is the actual problem that Jonathan Block and his colleagues faced when they sat down with the Titanoboa fossils and began trying to determine the animal's true size. They did not have a complete skeleton. Nobody has ever found a complete skeleton of Titanoboa. What they had were fragments, vertebrae mostly, some rib pieces, and partial elements from the skull region. Beautiful, well-preserved, unmistakably genuine fossil pieces, but not a whole animal. So how do you get from a bone to a body? The answer lies in a biological relationship that scientists had already documented carefully in living snakes. In modern boas and anacondas, the family of snakes most closely related to Titanoboa, there is a very reliable and consistent mathematical relationship between the size of the mid-body vertebrae and the total length of the animal. When scientists measure a large collection of modern boas and map their vertebra size against their body length, they find a very tight, very dependable correlation. Larger vertebrae mean longer snakes, and the relationship between the two numbers is consistent enough to be used as a formula. Think of it like this. Imagine you have never seen a particular model of car, but you find one hubcap from it in a junkyard. If you know the rule that governs how hubcap diameter relates to overall vehicle width for that manufacturer, you can calculate the width of the whole car from that single hubcap. You never have to see the full vehicle. The part tells you about the whole. That is exactly what the Titanoboa vertebrae did. They told scientists about the whole. When the measurements were run and the calculations completed, the result was an estimated body length of approximately 12.5 to 14 meters, with the best central estimate landing right around 13 meters. To put that in terms that you can feel physically, 13 meters is roughly the length of a large school bus. Not a short transit bus. A full-sized yellow American school bus. Imagine that entire length occupied by a living, breathing, moving snake, and you are beginning to approach Titanoboa. Now let us talk about weight, because length is one thing, but the weight of Titanoboa is where the true scale of this animal becomes visceral. Using the same body proportion methods applied to weight estimates from living relatives, scientists arrived at a figure of approximately 1,135 kilograms for an average adult Titanoboa. That is just over a metric ton, more than 2,500 pounds. The weight of a large automobile. Compare that to the green anaconda, the heaviest snake alive on Earth today. The largest reliably documented green anacondas weigh somewhere between 90 and 150 kilograms at the absolute maximum. That means Titanoboa was, at minimum, 7 to 8 times heavier than the largest snake alive today. In realistic terms, the comparison is probably closer to 10 times the weight of a large anaconda. That is not a modest increase. That is a different category of animal entirely. Now let us talk about the body itself. Not just its length, but its girth, its actual physical thickness. At its widest point, roughly in the midsection of the body where snakes are always thickest, Titanoboa's body diameter has been estimated at somewhere between 75 and 90 centimeters. Let us take the middle of that range and say roughly 80 centimeters across. That is about as wide as an adult man's shoulders. Not the shoulders of a slight man, the shoulders of a large, broad-shouldered man. Now imagine that width as the cross-section of a cylinder, and imagine that cylinder extending for 13 meters in both directions from your hands. That is the body of Titanoboa. That is what it looked like from the side when it was resting in shallow water. To appreciate this properly, consider what it would mean to stand next to one. If you were standing on a riverbank and a coiled Titanoboa were lying in the shallows nearby, the top of its body at the midpoint of its coil would reach roughly to your hip or perhaps your waist. Its head, when raised and alert, would be at chest height or above. And when it moved, the wave of its body would be something you would feel in the ground beneath your feet before you saw it coming. Now, how does Titanoboa compare to every other snake that has ever lived? Let us walk through the size hierarchy, from largest to smallest among the giants, because this comparison helps establish just how remarkable Titanoboa truly was. At the bottom of our giant snake list, you would place the king cobra, the longest venomous snake alive today, reaching perhaps 5 to 5.5 meters at the very most. Impressive, to be sure. Then comes the reticulated python, the longest living snake by measurement, with reliable records of individuals approaching 8 meters in exceptional cases. Then the green anaconda, which does not match the reticulated python in length, but exceeds it considerably in body mass. Then Gigantophis garstini, an extinct African giant snake from roughly 40 million years ago, estimated at 9 to 10 meters, which held the record for largest known snake before Titanoboa came along. And then, well above all of them, Titanoboa. There is no close second. The gap between Gigantophis and Titanoboa is almost as large as the gap between a reticulated python and a king cobra. Titanoboa was not slightly bigger than the previous record holder. It was in an entirely different category of existence. But here is where the science becomes truly extraordinary, and where the story of size connects back to the story of the world. Because the scientists who studied Titanoboa did not just use the fossil bones to calculate the animal's size, they reversed the calculation. They used the animal's size to calculate the temperature of the ancient world. Here is the logic, and it is elegantly simple once you understand the underlying biology. Cold-blooded animals, which includes all snakes, rely on their environment to regulate their body temperature. Unlike warm-blooded animals like us, they cannot generate heat internally. They absorb it from outside. This means that their metabolic rate, the speed at which their bodies process food and build tissue and carry out all the functions of life, is directly tied to the temperature of the environment they live in. A warm environment means a faster metabolism. A faster metabolism means faster growth. Faster growth sustained over the lifetime of an animal means a larger body. This relationship has been documented carefully in living reptile populations across different climates. The warmer the climate, the larger the maximum body sizes achieved by cold-blooded species living in it. Scientists call this relationship between temperature and body size in cold-blooded animals one of the most reliable patterns in all of biology, and it works in both directions. You can look at the temperature and predict the maximum size, or you can look at the maximum size and calculate backward to estimate the temperature. When the scientists applied this logic to Titanoboa, they found that for a snake of that size to exist, the average temperature of the tropical region it lived in must have been somewhere between 30 and 34 degrees Celsius. That is consistent with other lines of evidence about Paleocene tropical temperatures derived from entirely different scientific methods, including analysis of ancient plant fossils and chemical signatures in ancient ocean sediments. This is the moment that transforms Titanoboa from a remarkable fossil into something genuinely profound. A dead snake in a coal mine told us how hot the world was 60 million years ago. Not roughly how hot, not approximately. Within a meaningful range of precision, the bones of this animal function as an ancient thermometer, recording the climate of a world that no living creature has ever seen. That is the kind of beautiful, unexpected logic that makes science something more than just a collection of facts. It is the kind of discovery that changes the way you see the world, because it means that fossils are not just records of animals. They are records of the conditions that produced those animals. They are the world's diary, written in stone, waiting to be read by anyone patient enough and skilled enough to understand the language. And there is one more thing to say about the size of Titanoboa before we move on. Scientists have thought carefully about whether a snake could have been even larger. whether there might have been individuals bigger than our best estimates, whether future discoveries might push the numbers higher. The answer is probably not dramatically higher because of a fundamental physical constraint. A snake's skeleton must support its own weight. At extreme sizes, the forces acting on the spine and ribs become very significant. Moving a body this large requires an enormous amount of muscular energy. The larger a cold-blooded animal gets, the more food it needs to sustain itself. And there is a point at which the energy cost of maintaining and moving the body exceeds what the environment can provide, no matter how warm and productive that environment is. Titanoboa appears to have been operating very close to that limit. It was not just the biggest snake we know of, it was near the physical ceiling of what a snake can be. Chapter 4. Inside the monster. Every great predator is a machine. Not a machine in the cold mechanical sense, but in the sense that every part of it has been shaped, tested, refined, and perfected over millions of generations until it fits its purpose like nothing else could. The eyes of a hawk, the nose of a wolf, the speed of a cheetah, the venom of a cobra. These are not accidents. They are answers. Answers to specific questions that survival asks, answered in bone and muscle and scale and tissue across an almost unimaginable span of time. Titanoboa was a machine of extraordinary elegance and power, and to truly understand it, we need to go inside it. We need to build it from the bones outward and understand not just what each part was, but what it was for. Let us begin with the skeleton. The spine of a snake is one of the most beautiful structures in all of vertebrate biology. Unlike a human spine, which is designed primarily for upright stability and the support of a two-legged body, a snake's spine is designed entirely for three-dimensional flexibility and locomotion. It is a chain of interlocking joints, each capable of independent movement, each adding its small increment of flexibility to create a total range of motion that no other vertebrate comes close to matching. Titanoboa had something in the neighborhood of 250 vertebrae, though the exact number remains estimated since no complete specimen has been found. Each vertebra was connected to its neighbors by a remarkable joint system called the zygosphene and zygantrum, words that are simply the technical names for the ball and socket locking mechanism that snakes developed early in their evolution and have kept ever since. This system gives each joint tremendous lateral flexibility, while maintaining enough structural integrity to bear the animal's weight and transmit the forces of locomotion. For Titanoboa, with a body the length of a school bus, this meant that the snake could bend at essentially any point along its body, at essentially any time, coordinating hundreds of independently moving joints into smooth, wave-like patterns of motion that we can only fully appreciate by watching large modern constrictors move and then imagining it scaled up to something 10 times the mass. The ribs of a snake are not what we typically think of when we think of ribs. In mammals, ribs are primarily protective structures, curved bones encasing the chest cavity and shielding the heart and lungs. In snakes, the protective function exists, but is secondary to a locomotion function that most people never think about. The ribs of a snake articulate with the vertebrae in a way that allows them to move independently, and they work together with the large ventral scales on the belly to create the gripping, pushing, flowing motion that moves the snake's body across surfaces. Think of it as hundreds of tiny legs, all working in precise sequence. No single rib does much, but 250 ribs, coordinated perfectly by a nervous system evolved for exactly this purpose, can move over a ton of muscle and bone across a riverbank with surprising effectiveness. Let us talk about how Titanoboa actually moved, because locomotion in a snake this large is a genuinely fascinating problem. Modern snakes use several different styles of movement depending on the situation they are in. The most common is lateral undulation, the classic sideways wave pattern that most people picture when they think of a snake moving. Then there is rectilinear motion, sometimes called caterpillar motion, in which the snake moves in an essentially straight line by using its ventral scales and the muscles connecting them to the ribs to push the body forward section by section. This is how very large, heavy snakes often prefer to move on flat surfaces, because it requires less energy expenditure than full lateral undulation. Then there is concertina motion, used in tight spaces, where the snake anchors part of its body and extends another part forward, then anchors the extended section and pulls the rear up. And then there is the specialized sidewinding used in loose substrates like sand. For Titanoboa, the most likely primary modes were rectilinear motion on land, where sheer mass made the energetic efficiency of caterpillar movement attractive, and lateral undulation in water, where the resistance of the fluid provided the push-off point the body needed for powerful forward movement. In water, the physics changed in Titanoboa's favor dramatically. A body weighing over a ton is not easily moved on land even with powerful muscles. But in water, buoyancy reduces the effective weight considerably, and the same mass that makes terrestrial locomotion slow and expensive becomes an advantage in the water, providing inertia and momentum that makes each powerful lateral undulation cover significant distance. Scientists believe that Titanoboa was primarily aquatic, spending the majority of its time in or near the rivers and swamps of the Sarajan system. This is consistent with what we know about the ecology of its living relatives, the largest of which, particularly the green anaconda, are strongly associated with water. It is also consistent with the fossil evidence. The Sarajan Formation is a river and floodplain deposit. The animals found in it, including Titanoboa, were animals of the water's edge. Now let us move to the head and jaw, because this is where the engineering becomes truly impressive. The skull of a snake is nothing like the skull of a mammal. A mammal skull is a rigid box, firmly joined at most of its seams, designed for stability and the transmission of biting force. A snake skull is the opposite of this in almost every way. It is a loose collection of bones, connected by elastic ligaments, designed not for stability but for extraordinary, almost unlimited gape, the ability to open the mouth so wide that the animal can swallow prey far larger than its own head appears possible. The lower jaw of a snake is divided into two halves. In most vertebrates, the two halves of the lower jaw are fused at the front into a single rigid unit. In snakes, they are separated, connected only by an elastic ligament that allows the two halves to spread apart independently of each other. This is not a small detail. It means that the jaw can accommodate prey that is wider than the snake's entire skull would normally suggest. But it goes further than this. Snakes have what is sometimes described as a four-part jaw system. The upper jaw divided into two sections that can move somewhat independently, and the lower jaw divided into its two separate halves. When a snake is swallowing, the different sections of this jaw system work in alternating sequence, effectively walking the prey down the throat in a ratcheting motion. The prey is not so much pushed down as it is progressively engulfed by a mouth that keeps advancing over it. For Titanoboa, this jaw system could handle prey of sizes that are genuinely difficult to imagine. A 5-meter crocodilian, an enormous turtle, a fish weighing hundreds of kilograms. The jaw architecture was not a limiting factor in what Titanoboa could eat. The limiting factors were elsewhere in the body, and they were generously sized. The teeth of Titanoboa deserve a moment of attention because they are often misunderstood. Titanoboa was not venomous. There are no venom delivery structures in its fossil remains, and its closest living relatives are constrictors, not venomous snakes. What Titanoboa had instead was rows of curved, relatively slender teeth pointing backward, angled toward the throat. These are not designed for killing. They are designed for one specific purpose: which is to make escape from the mouth mechanically impossible. Once those teeth are engaged on prey tissue, any movement the prey makes in the direction of escape simply drives the teeth deeper. The only direction those backward curving teeth permit is forward, into the throat, toward the stomach. There is an almost philosophical finality to the design. The moment the teeth engage, the outcome is determined. The tongue of Titanoboa functioned exactly as it does in all modern snakes, as a remarkable sensory organ. This is worth explaining because the snake tongue is so different from the human idea of a tongue that it takes a moment to understand properly. When you see a snake flicker its tongue in and out, it is not tasting its food and it is not threatening you. It is smelling you, or rather, it is doing something that combines smelling and tasting in a way that has no precise equivalent in human sensory experience. The forked tongue picks up microscopic chemical particles from the air and from surfaces and carries them to two tiny openings in the roof of the mouth called the Jacobson's organ, or more formally, the vomeronasal organ. This structure analyzes the chemical information and sends signals to the brain that give the snake a detailed, three-dimensional picture of its chemical environment. The fork in the tongue is important because the two tips of the fork are spatially separated. They pick up slightly different concentrations of the same chemical from slightly different positions. The brain compares these two readings and can determine not just what the smell is, but which direction it is strongest, allowing the snake to navigate toward or away from the source with considerable precision. In the murky, low-visibility world of the Sarajan rivers, where sight would have been almost useless and sound transmission through water unreliable, this chemical sense was Titanoboa's primary connection to the world around it. It knew what was in its environment with a completeness and precision that we cannot really appreciate from within our own visual dominant sensory experience. There is also a strong possibility that Titanoboa possessed another sensory capability that some of its modern relatives have, which is the ability to detect heat directly. Many members of the boa family have small pit organs along their lips that are sensitive to infrared radiation, essentially to radiated body heat. These organs allow the snake to detect the presence of a warm-bodied animal even in complete darkness, even through dense vegetation, even in water where chemical signals might be dispersed. They are nature's thermal imaging system. We cannot say with certainty that Titanoboa had these pit organs. The delicate lip tissues where they would be found do not fossilize well. But given the close relationship between Titanoboa and the modern boas that do possess them, and given the environmental logic of hunting in near-total murk and darkness, it is entirely reasonable to think that Titanoboa could sense the body heat of its prey from a considerable distance before any other sense was engaged. It could feel the warm blood of a passing crocodilian in the water around it, the way a person standing near a campfire can feel the heat on their skin before they can clearly see the flames. The scales of Titanoboa, while not directly preserved in the fossils, can be confidently inferred from its relatives. Snake scales are not separate structures the way fish scales are. They are folds of the same continuous skin, stiffened and shaped differently in different parts of the body for different purposes. The large, smooth, wide ventral scales on the belly are the primary locomotion scales. They create the gripping surface that interacts with the ground in rectilinear movement. The smaller dorsal scales on the back are more protective than functional, forming an overlapping layer of toughened skin over the back and sides. The color of Titanoboa in life is something we can only guess at. Fossilization preserves structure but not color. But color in large aquatic predators follows very consistent patterns across many different animal groups, driven by the same camouflage logic regardless of the species. Dark on top, lighter underneath. This pattern, called countershading, makes an animal in the water less visible from above, where its dark back blends with the dark water below, and less visible from below, where its lighter belly blends with the sunlit water above. It is a pattern used by sharks, crocodiles, large fish, and anacondas, and it would make perfect functional sense for Titanoboa in the murky rivers of the Paleocene. Inside the body, Titanoboa's organ systems were those of a large boa, magnified enormously. Like all boas and pythons, it had 2 lungs, but the left lung was vestigial, a tiny remnant of an organ that evolution had decided was no longer necessary when the right lung expanded to occupy most of the body cavity. The right lung was enormous, a long, sac-like structure that extended for a significant portion of the body's length, providing the respiratory capacity needed for an animal of this size. The digestive system of a large constrictor is one of the most remarkable examples of biological efficiency and flexibility anywhere in the animal kingdom. Between meals, the digestive organs actually shrink. The stomach reduces in mass. The intestinal lining thins. The liver reduces its activity. All of this is an energy conservation strategy for an animal that may go weeks or months between large meals. But when a meal arrives, something remarkable happens. Within a day or two of swallowing large prey, the metabolic rate of the snake increases dramatically. The heart rate goes up significantly. The digestive organs rapidly regrow to their full operational size. The liver accelerates. Digestive enzymes flood the stomach cavity. This rapid metabolic upswing allows Titanoboa to digest a meal of staggering size in a matter of days to weeks. Everything. The bones, the scales, the shell fragments, almost everything is broken down and absorbed. What cannot be digested is eventually compressed into compact waste matter and expelled, but the efficiency of digestion in large constrictors is so high that this waste is a small fraction of the original meal. The heart of Titanoboa faced a genuinely remarkable engineering challenge. The animal's body was over 13 meters long. The heart sat in the forward part of the body, roughly a quarter of the way back from the head. Blood pumped from that heart had to travel to the tail and back, a round trip of roughly 20 meters of circulation, including the return journey. This required significant blood pressure. But in large constrictors, the heart is capable of generating exactly this pressure, and its position within the body cavity is not entirely fixed, allowing for some positional adjustment depending on the snake's posture. One last thing to understand about the internal biology of Titanoboa is the concept of gigantothermy. This term describes a phenomenon observed in very large, cold-blooded animals where sheer body mass creates a passive thermoregulatory effect. Here is the logic. All objects absorb heat from their environment. They also lose heat to the environment. The rate at which heat is absorbed is proportional to the surface area of the object. The rate at which heat is lost is also proportional to surface area. But the amount of heat stored in an object, and therefore how long it stays warm, is proportional to its volume, or its mass. A very large animal has a lower ratio of surface area to volume than a small animal. This means it absorbs heat slowly, but it also loses heat very slowly. Once a warm day has heated Titanoboa's enormous body mass to its preferred operating temperature, that body mass acts like a thermal reservoir, staying warm long into the cool of the night, maintaining the metabolic activity needed for digestion and basic body function even when the air temperature drops somewhat. This is the same physical principle that is thought to have helped large dinosaurs maintain relatively stable body temperatures despite being cold-blooded. And it is one more way in which Titanoboa's extraordinary size was not just a consequence of its environment, but an active asset that made it more effective as a living organism. Chapter 5. The Predator at Work. It is 60 million years ago. The hour is somewhere near midday. The sun above the Paleocene tropics of what will one day be Colombia is not particularly visible because the sky is heavy with moisture and the light that reaches the forest floor is diffuse and green, filtered through layer upon layer of enormous leaves. The temperature at the water's edge is somewhere around 33 degrees Celsius. The air smells of mud and vegetation and warm water. The river here is perhaps 40 meters wide at this crossing. Not deep. A meter or a meter and a half over most of the bottom. The current is lazy and slow, and the water is the color of strong tea, brown with tannins leached from the rotting plant matter that carpets the riverbed. At the near edge of the river, where the bank slopes gently down into the water and the mud is soft and thick, something is lying very still. From above, it looks like the bottom, like a series of long, dark, parallel ridges of mud, perhaps a collection of submerged logs. Nothing that moves, nothing that catches the eye. The water flows over it with barely a ripple, but it is breathing. Slowly, barely perceptibly, the body of Titanoboa rises and falls with each long breath. The tongue slips out into the water at intervals, picks up the chemical signature of everything that has passed this way in the last several hours, draws it back to the Jacobson's organ, and the brain assembles the picture. Fish have been through here recently, large ones. A dirosaurid crocodilian, perhaps 3 meters long, came this way this morning and is somewhere upstream, and something larger, something moving slowly through the vegetation on the far bank, something that smells different and warm, is approaching the water's edge from the other side. Titanoboa waits. This is what it does, and it does it with a completeness and an absence of impatience that no mammalian predator can approach. There is no fidgeting. There is no restless movement. There is only the slow breath, the flickering tongue, and the patient processing of information. The snake has perhaps been here for 2 days. It will stay until the right moment presents itself. On the far bank, a large dirosaurid crocodilian is picking its way through the vegetation toward the water. It is just over 4 meters long, powerfully built with a long, narrow snout evolved for catching fish. It has no awareness of what is waiting in the shallows ahead of it. Why would it? In this ecosystem, the crocodilian is a significant predator in its own right. It has few concerns. It enters the water with barely a splash, settles into the crossing, and begins to move toward the deeper channel. What happens next takes about 3 seconds. The tongue in the mud detects the displacement of the water. The change in pressure waves traveling through the water carries information to sensory receptors along the snake's jaw and body. Something large is moving in the shallows, perhaps 4 meters distant, moving this direction. The chemical signature is suddenly strong, close, vivid. The first movement is the head, just the head, lifting smoothly from the mud in a direction that intercepts the crocodilian's path, not where the prey is now, but where it will be in 1 more second of movement. The rest of the body, those 13 meters of coiled muscle and bone, begins to engage in precise sequence, the coils tightening, the whole system loading itself for the explosive release. Then the body moves. It moves as a wave, not a single lunge like a striking rattlesnake, but a rolling wave of force that covers distance in a way that seems impossible for something this large. The head arrives at the crocodilian in a fraction of a second. The teeth engage, and then the coils follow. The crocodilian has no time to react meaningfully. The first coils are already wrapping before its nervous system has finished processing what has happened to it. The water churns briefly, then it settles. Now let us understand what constriction actually does, because the popular image of a constricting snake slowly crushing its prey to death by suffocation is not quite accurate. Modern research has refined our understanding significantly, and what it shows is at once more efficient and more absolute than the old picture. When a large constrictor wraps its coils around prey, The pressure it applies is distributed across the entire surface in contact with the prey's body. This pressure is not primarily aimed at the lungs. It is aimed at the circulatory system. When sufficient pressure is applied uniformly to a body, blood flow to and from the heart is interrupted. The heart, which relies on the difference between the pressure inside it and the pressure outside it to draw blood in and push blood out, cannot function against the pressure of the coils. It stops. The brain, deprived of oxygenated blood within seconds, shuts down. Modern studies measuring the constricting force of large anacondas have found pressures of roughly 90 pounds per square inch, which is comparable to the pressure felt at the bottom of about 60 meters of water. Titanoboa, with roughly 10 times the body mass and correspondingly larger muscles and coils, would have applied forces that put this figure into a different category entirely. The crocodilian's heart stops within seconds. There is no prolonged struggle. There is no slow suffocation. There is a brief, violent engagement, and then stillness. Titanoboa holds on for a short time after the prey stops moving. This is standard behavior in large constrictors, and the logic is simple. The snake's sensors detect the cessation of the prey's heartbeat directly through the pressure of the coils, the change in vibration, the sudden absence of the pulse that was there a moment ago. Only when it is certain that the prey is dead does it begin to release the coils and reorient toward the head. Swallowing a 4-meter crocodilian is not a quick process. It takes hours. Titanoboa works the jaw system forward over the prey methodically, the alternating sections of the jaw advancing in sequence, the body expanding to accommodate what is passing into it, the muscles of the throat and neck working continuously. The prey goes in head first. This is not arbitrary. Head first orientation aligns the limbs and other protrusions of the prey in the direction they fold most easily, making swallowing mechanically possible. After several hours, it is done. What was a 4-meter crocodilian is now an elongated bulge in the body of Titanoboa. The snake moves to a warm, sunny stretch of riverbank, spreads its coils as widely as possible to maximize the surface area absorbing the sun's heat, and lies still. The metabolic response begins immediately. The heart rate increases. The stomach walls thicken rapidly as new digestive tissue grows. Acids begin to flow. The liver ramps up to handle the products of digestion. Over the next several days, possibly the next 1 to 2 weeks, the crocodilian is systematically broken down and absorbed. The bones soften. The tough scales are processed by the highly acidic stomach environment. The muscles dissolve into amino acids that are absorbed and rebuilt as Titanoboa's own muscle. Nothing is truly wasted. When it is finally done, Titanoboa may not need to hunt again for weeks, possibly longer. This is one of the extraordinary advantages of cold-blooded metabolism. A warm-blooded predator of comparable mass, a large mammalian carnivore for instance, would need to eat continuously, every few days at minimum, to maintain its body temperature and metabolic rate. Titanoboa has no such demand. It eats when the opportunity presents itself, and then it processes in perfect stillness until the need arises again. But let us talk about the full menu, because crocodilians were not the only prey item in the Sarajevo system. The giant turtles, the carbonomes, present an interesting problem that scientists have thought about carefully and honestly acknowledged the uncertainty around. A turtle with a shell 1.5 meters long and made of genuinely hard bone and keratin is not something a snake can simply engulf in the standard way. Titanoboa's jaw system, for all its remarkable flexibility, was not designed to crush bone. The most likely answer involves the availability of juvenile turtles. Young turtles, before their shells have hardened fully, are much softer and more manageable. They are abundant, relatively slow, and nutritionally dense, A snake of Titanoboa's sensory acuity and patience would have had little difficulty locating and consuming young turtles in significant numbers. The giant adults perhaps were largely left alone, an unusual coexistence between two very large animals sharing the same water. Though there is a qualification worth adding here. We cannot say for certain that Titanoboa never attempted large adult turtles. Constriction creates forces that are extraordinary, and the anatomy of a constricting snake does not require the prey to be swallowed whole. What it requires is that the prey be immobilized. Some dismantling, some selective consumption may have been within Titanoboa's behavioral repertoire. We simply do not know. The large fish of the Karajan system were almost certainly regular prey, particularly for ambush situations near river crossings and in shallow pools. Large fish weighing tens of kilograms would have been entirely within Titanoboa's capacity and would have represented a relatively low-risk meal compared to the dynamically dangerous crocodilians. The ambush strategy works particularly well in the kinds of shallow, warm crossing points where large fish aggregate. Now let us think about reproduction, because no discussion of an animal's life is complete without understanding how it made more of itself. Titanoboa belonged to the boid family of snakes, the boas and their close relatives. And boas, unlike many other snake families, do not lay eggs. They give birth to live young, carrying the developing offspring internally through a gestation period that can last several months. Modern boa constrictors give birth to litters ranging from 10 to perhaps 60 young in very large individuals. Green anacondas have been recorded delivering litters of up to 80 young. For Titanoboa, we can reasonably infer a similar reproductive strategy. Live birth, a litter of probably dozens of young, and those young, even at birth, were already significant animals. Based on body proportion estimates, a newborn Titanoboa was probably between 1 and 1.5 meters long, already capable of hunting, already a predator in a world where everything was large. There is something almost touching about this image, if you allow yourself to think about it. Dozens of meter-long snakes dispersing into the Karajan wetland system, each one already carrying in its body the blueprint for something that, given time and food and warmth, could grow into the largest snake the world has ever known. The social life of Titanoboa, to the extent that large constrictors have a social life, was almost certainly minimal. Modern large boas and anacondas are solitary animals. They occupy enormous individual home ranges, hundreds of square kilometers in some cases for the largest anacondas. They come together briefly for mating, which in the boa family involves complex competitive behavior among males competing for access to females. Then they separate and remain alone for the rest of the year. Titanoboa almost certainly followed this same pattern. In the vast river system of the Paleocene Karajan, individual animals may have had virtually no contact with each other for months at a time, their territories defined and maintained by chemical signaling, by the scent trails they left in the environment, readable to others of their kind as precisely as a posted sign. In any given stretch of river in the Karajan system, there may have been only a handful of adult Titanoboas, each one sovereign in its section of water, each one the final word in every predator-prey interaction that occurred within its range. Chapter 6. The River Kingdom. Stand back for a moment. Step away from the close-up view of Titanoboa as an individual animal and try to see the whole picture. What you are looking at when you see the Karajan ecosystem in its entirety is not just a collection of large animals sharing a warm river. You are looking at a complex, interwoven system of relationships. A system that had been assembling itself for millions of years in the peculiar conditions of the Paleocene tropics and had arrived at a kind of balance. Not a static balance, not a balance that never changed, but the dynamic, self-adjusting kind of balance that all functioning ecosystems maintain for as long as their conditions remain stable. Titanoboa was at the top of this system, but the top of a pyramid only exists because of everything below it. Without the fish, without the turtles, without the crocodilians, without the plants that fed the fish and the insects and the small mammals that fed the crocodilians, Titanoboa had nothing. It was the summit, but the mountain was everything else. Let us walk through this ecosystem from the ground up. At the very foundation of the Sarajevo system were the plants, and the plants of the Paleocene tropics were extraordinary producers. In the absence of seasonal cold, in the constant heat and moisture of a greenhouse world, tropical plants grew year-round without interruption. The forest canopy was continuous and dense, built from trees and palms and giant ferns that competed fiercely for light in the upper layers while casting everything below into warm, humid shadow. This continuous productivity meant that the biomass of the Sarajevo forest was staggering. More plant matter per square kilometer than perhaps any comparable area of modern tropical forest. More leaves, more fruit, more seeds, more root mass. And all of that plant productivity was the energy source that powered everything else in the system. The primary consumers, the animals that ate the plants directly, included insects of considerable size and diversity, early birds that had evolved from the lineages that survived the end Cretaceous extinction, small primitive mammals foraging in the undergrowth and the lower branches of trees, and crucially, large fish feeding on the plant matter, and small organisms that entered the rivers from the surrounding forest. Fish are efficient converters of plant-based aquatic productivity into animal tissue, and in a river as productive as the Sarajevo system, the fish populations were dense and large. Above the primary consumers were the secondary consumers. This is where the system begins to look more familiar. Large fish eating smaller fish, early turtles, including the juveniles and subadults of the giant carbonemys, feeding on fish, aquatic plants, and invertebrates. The smaller crocodilians, hunting fish and smaller aquatic animals with their slender snouts. Early birds of more significant size catching fish from the surface. This mid-level of the food web was rich, diverse, and constantly in motion. And above all of this, at the apex of the pyramid, were two groups of large predators. The larger dirosaurid crocodilians, which were apex predators in their own right for animals of their size range, and Titanoboa, which was the apex predator for everything. The dirosaurids deserve a moment of attention. Several species have been recovered from Sarajevo, and they represent a group of crocodilians quite different from the animals that modern people associate with that name. They were slender-snouted, fast-swimming, primarily fish-hunting animals. Think of them as something between a modern gharial and a small crocodile. They could reach 4 to 5 meters in length in the largest specimens, which is significant. But alongside Titanoboa, they were not at the top. One of the questions that scientists have found genuinely interesting about the Sarajevo ecosystem is the nature of the relationship between these crocodilians and Titanoboa. Were they competitors? Were they prey? Were there situations where the crocodilian was the hunter and Titanoboa was not safe? The most honest answer is that this relationship was probably complex and context-dependent. A very large dirosaurid, an aggressive adult at the peak of its physical condition, in water deep enough to maneuver effectively, might have posed a genuine challenge even for Titanoboa. Crocodilian biting force is extraordinary. Their thrashing ability in water is formidable. And for a large constrictor, any injury that prevents it from hunting effectively is a potentially fatal situation over the long term. But in the context of the overall size hierarchy, Titanoboa was almost certainly the dominant animal in the system. A subadult crocodilian, or an adult in shallow water where it could not maneuver freely, was prey. The fossil evidence at Cerrejón, while not providing a direct picture of a Titanoboa feeding on a crocodilian, is entirely consistent with this interpretation. Both animals lived in the same space. One was the apex predator, the other was not. Now let us talk about Carbonemys cofrini, the giant turtle, in more depth. Because this animal's relationship with Titanoboa is one of the most visually striking aspects of the entire Cerrejón story, and it deserves to be given its proper due. Carbonemys was named in 2012 after being found in the same Cerrejón deposits as Titanoboa. Its name means coal turtle, honoring the coal mine where it was found. The shell was roughly 1.5 meters long, which makes it comparable to the largest freshwater turtles known from anywhere in the fossil record. It was a pleurodiraen turtle, which means its neck folded sideways when it retracted into the shell, rather than straight back the way most familiar turtles do, and it was an animal of considerable age when it grew to its maximum size. Turtles grow slowly. A Carbonemys with a 1.5-meter shell had probably been alive for decades. The image of these two giant animals sharing the same warm, murky rivers is one of the most evocative in all of ancient natural history. A giant turtle and a giant snake, both the largest of their kind that have ever existed in the fossil record, living alongside each other in the same ecosystem, breathing the same warm air, moving through the same brown water. Were they enemies? Competitors? Were they simply large animals that occupied such different ecological roles that they barely interacted? We genuinely do not know. What we know is that they coexisted for what appears to be hundreds of thousands of years, which suggests that whatever their relationship was, it was compatible with the long-term survival of both. The small mammals of the Cerrejón deserve a brief but important mention, because their story in this chapter is really the setup for the next one. Early Paleocene mammals were small and inconspicuous. The largest were probably no bigger than a large domestic cat, and most were considerably smaller. They were fast-breeding, adaptable, wide-ranging in their diets, and largely invisible in the grand drama of the Cerrejón giants. But they were there, moving in the undergrowth, up in the trees, in the root systems of the great palms, eating insects and fruit and seeds, occasionally falling prey to a crocodilian or a large bird, and breeding, always breeding. Their relatively fast reproductive cycles, compared to the slow generation times of the giant reptiles, meant that their populations could respond quickly to changes in conditions. Small changes in food availability, small changes in temperature, small changes in the habitat, and the mammals could adjust within a few generations. The giant reptiles, the snakes, the turtles, the crocodilians, were built for stability. They were optimized for the world as it was. The mammals were built for change. They were generalists, not specialists. And generalists, as natural history has shown over and over again, are the ones who survive the transitions between worlds. The Cerrejón ecosystem at its peak was a system of extraordinary richness and complexity. Titanoboa was its crown. The rivers that ran through it were some of the most biologically productive bodies of water in the history of this planet. And the whole magnificent structure had been running for somewhere between 1 and 2 million years by the time anything began to change. 1 to 2 million years. Modern human civilization, from the first cities to the present day, is roughly 10,000 years old. Our species, Homo sapiens, has existed in recognizable form for perhaps 300,000 years. Titanoboa reigned as apex predator in the Cerrejón system for a span of time that dwarfs both of those numbers. It was not a brief flash of evolutionary success. It was a long, stable, successful reign by any measure that natural history offers. And then something began to shift. Chapter 7. The Fall. Every story that is told honestly must include the ending. And the ending of Titanoboa's story is not a triumphant one. It is something quieter and more melancholy than that. Something that asks us to sit with a difficult truth about the nature of success in the natural world. The truth is this: being perfectly adapted to one world is not the same as being safe. It is not the same as being permanent. It is not the same as being protected. Perfection, in the biological sense, is a snapshot. It is an answer to a question that the environment is asking right now. But the environment is not static. The questions change, and sometimes they change in ways that no amount of strength or size or sensory acuity can answer. For Titanoboa, the question changed around 58 million years ago, and it changed in a direction that Titanoboa, for all its extraordinary design, had no answer to. The question was temperature. The answer was cooling. To understand how this happened, we need to go back to the broader story of Earth's climate during the Paleocene and into the epoch that followed it, called the Eocene. The extreme warmth of the Paleocene, that greenhouse world of tropical forests reaching toward the poles and warm oceans and no ice caps, was not permanent. It was a phase, a long phase to be sure, lasting millions of years by our counting, but a phase nonetheless in the longer story of Earth's climate history. Beginning around 58 to 56 million years ago, the global climate began what would prove to be a very long, very gradual shift toward cooler conditions. It was not sudden. There was no single moment, no dramatic event, when the temperature dropped sharply. There was instead a slow, steady drift, year by year, century by century, millennium by millennium, toward a somewhat less extreme warmth. There was, interestingly, one brief interruption in this cooling trend. About 56 million years ago, there was a sudden and dramatic spike in global temperatures called the Paleocene-Eocene thermal maximum, a relatively short period during which temperatures jumped sharply upward again before resuming the long-term cooling trend. This event, driven by a massive release of carbon into the atmosphere, was one of the most significant climate disruptions in the last several hundred million years of Earth's history. But even this temporary warming spike did not save Titanoboa. By the time of the Paleocene-Eocene thermal maximum, the ecosystem that had supported the giant snakes was already changing in other ways. The primary force of change alongside the cooling climate was geological. The Andes Mountains were beginning to rise. The story of the Andes is a very long story, because mountain building is a process that operates on timescales that make even the lifespan of Titanoboa look brief. The Andes are the result of the South American tectonic plate, the massive slab of rock on which the continent sits, colliding with and overriding the Nazca plate, the oceanic plate to its west. This collision, which is still ongoing today, causes the rock at the western edge of South America to buckle and compress and push upward. Mountains grow, slowly, a centimeter at a time, over millions of years. At the time of Titanoboa, the Andes were barely a whisper of what they would become. But over the tens of millions of years following Titanoboa's extinction, they grew dramatically. And as they grew, they transformed the climate and the hydrology of northern South America in ways that were irreversible. Rivers changed their courses. Rain patterns shifted as the mountains intercepted moisture coming from the west. The flat, hot, low-lying swamp world of the Sarajevo began to transform slowly and inexorably into something different. For Titanoboa, these changes operated through a very direct mechanism. As temperatures dropped, even by a few degrees on average, the metabolic advantage that had allowed the snake to maintain such an enormous body mass began to erode. A cold-blooded animal in a slightly cooler world processes food a little more slowly, grows a little more slowly, requires slightly less food to maintain its body, but also has slightly less energy available for the physical demands of hunting and reproduction. The critical threshold is not precisely known. We cannot say that at exactly 31 degrees Celsius Titanoboa was viable and at exactly 30 degrees it was not. The real world does not operate with those kinds of clean boundaries. What we can say is that as the average temperature of the Sarajevo region declined from the extreme highs of the early Paleocene towards somewhat more moderate levels, the upper size limit for cold-blooded animals declined with it. The temperature-size relationship that allowed a 13-meter snake to exist required a specific range of warmth, and that range was narrowing. And there was a compounding problem. Because it was not just the temperature that changed, the whole system changed. As the climate cooled slightly and the early Andes began to affect rainfall patterns, the extraordinary productivity of the Paleocene forest began to diminish. Not dramatically, not all at once, but measurably. The plants grew a little less abundantly. The rivers carried slightly less nutrient load. The fish populations were somewhat less dense. The crocodilians had somewhat fewer opportunities, and at the very top of this food pyramid, Titanoboa found that its prey base was thinning. This is the merciless arithmetic of apex predation. The apex predator is always the most vulnerable to any decline in the productivity of the system below it. Every reduction in the fish population reduces the crocodilians slightly. Every reduction in the crocodilians reduces the food available to Titanoboa slightly more. Small changes at the base amplify as they move up the pyramid. By the time a change in productivity reaches the apex, it has been multiplied through every level. At the same time, the mammals were beginning their own story. In a warming world, the cold-blooded giants had dominated. In a slowly cooling, more seasonal, more variable world, the advantages shifted. Warm-blooded animals, animals that generate their own heat and can maintain consistent metabolic activity regardless of the external temperature, were becoming more competitive. They could hunt in the cool of early morning when a large cold-blooded snake was still warming up. They could remain active year-round without the seasonal slowdown that affects even tropical reptiles when temperatures dip. They could fill ecological niches that had previously been occupied by large reptiles, and they could do it in a wider range of conditions. The mammals did not defeat Titanoboa. That is too dramatic a framing. They simply moved into spaces that were left empty as the giant reptiles declined for other reasons. But their increasing diversity and the increasing efficiency of their occupation of those spaces made recovery harder for the cold-blooded giants. What the end of Titanoboa looked like in real time is something that no fossil record can show us directly. Fossils preserve moments, not trends that happen over tens of thousands of years. What we can say is that the large snake fossils in the Sarajevo Formation thin out and disappear over a span of geological time that represents perhaps hundreds of thousands of years of gradual decline. There was no catastrophe, no asteroid, no volcanic winter, no plague, just a slow, grinding mismatch between a superbly designed animal and a world that was quietly, persistently becoming less suited to it. Each generation of Titanoboa may have been slightly smaller than the one before, slightly fewer young surviving to adulthood, slightly fewer adults reaching the maximum size that their predecessors had achieved, the population thinning across its range, individual animals living out their full lifespans in relative isolation, their territories no longer adjacent to others of their kind as they once might have been, finding fewer and fewer mates. And then, somewhere in the tropical forests of the ancient Sarajevo, in a world that was still warm and still rich and still recognizable as the world that had produced this magnificent animal, the last Titanoboa lived out its years and died. Nobody saw it. There was nobody to see it. In a world still 60 million years removed from anything like a human observer, the death of the last individual of the most extraordinary snake that ever lived was a perfectly silent event. The body sank into the mud of a warm river. The bones settled into the sediment. The river covered them over, and the world moved on, utterly indifferent to what it had just lost. There is something in that image that asks for a moment of quiet reflection. This was not a small achievement that ended. This was a million-year reign. This was an animal that had solved, as completely as any animal in the history of this planet, the problem of how to be a large predator in a warm, rich, aquatic ecosystem. It had solved it with such thoroughness that nothing came close to it for its entire tenure. And it was ended not by violence, not by competition, not by disease, but by the slow drift of the world's temperature downward by a handful of degrees. That is the lesson written in these bones. Perfection is not permanence. The world changes, and the world does not ask for permission. Chapter 8. The warning in the bones. We have come a long way together in this story. From a coal mine in Colombia to the deep past of 60 million years ago. From the biology of a single remarkable bone to the full picture of an entire lost world. From the size of an animal to the temperature of a planet. And now, in this final chapter before we close, we need to make a turn. Because the story of Titanoboa is not purely a story about the past. It is a story that speaks with quiet but unmistakable urgency to the present moment. To the world we are living in right now. Let us begin with the science, and let us be precise about it because precision matters here. The size of Titanoboa, as we have discussed, was used by scientists as a biological thermometer for the ancient world. The logic of that calculation is solid and well tested. For a cold-blooded animal to grow to the size Titanoboa achieved, the average temperature of its tropical environment must have been in a specific range. Scientists calculated that range to be approximately 30 to 34 degrees Celsius for the average air and water temperature of the Sarajevo region during Titanoboa's time. Other independent lines of evidence, from the chemistry of ancient ocean sediments to the types of fossil plants found in Paleocene formations around the world, confirm that the global average temperature during the Paleocene was somewhere between 6 and 10 degrees Celsius, higher than the global average temperature of the world, as it was in the 20th century. Now let us hold those numbers alongside some other numbers. Current scientific projections, based on the continuing trajectory of greenhouse gas emissions and climate system modeling, suggest that global average temperatures may rise by somewhere between 2 and 4 degrees Celsius by the end of this century compared to the pre-industrial baseline. Some projections are more conservative, some are less. There is genuine scientific debate about the precise range, but the direction is not debated. The direction is warming. 2 to 4 degrees of global average warming is not the same as the 6 to 10 degrees that separated our recent climate from the Paleocene. We are not heading back to Titanoboa's world in any simple sense. The pace is different, the starting conditions are different, and the ecosystems that exist today are calibrated to conditions very different from those of 60 million years ago. But here is what Titanoboa teaches us about what warming means for living things. The rules that made Titanoboa large are still operating. They have never stopped operating. The relationship between ambient temperature and the maximum body size of cold-blooded animals is a biological law, as reliable as any law in physics. It applies now as surely as it applied 60 million years ago, and scientists studying living reptile populations have begun to document exactly what this law predicts. Modern anacondas in the Amazon basin have shown measurable increases in maximum recorded body lengths over the past several decades. Researchers studying these populations are careful not to make simple causal claims because animal populations are complex and many factors affect body size. But the correlation between warming water temperatures and larger anaconda body sizes is there in the data. It is consistent with what the biology predicts, and it is worth paying attention to. More broadly, reptile populations across the globe are expanding their ranges in response to warming. Species that were historically limited to tropical or subtropical zones are being recorded further north and further south than they were decades ago. The warm weather window that allows cold-blooded animals to be active, to feed, and to grow is lengthening in many regions. The consequences of this ecologically are only beginning to be understood. This is not a disaster story. Let us be clear about that. The changes happening now are not producing new Titanoboas. The timescales for evolutionary responses to climate are far longer than a few decades or even a few centuries. What Titanoboa tells us is not that warming will produce monsters. What it tells us is that warming changes the fundamental rules of what is possible in living systems. It changes the size, the distribution, the metabolism, and the ecological role of cold-blooded animals. It changes the competitive balance between warm-blooded and cold-blooded species. It changes which animals thrive and which ones struggle. And here is the deeper, quieter warning in the Titanoboa story. The Sarajevo ecosystem was extraordinarily rich and productive during the Paleocene. The warmth generated enormous amounts of plant life, which generated enormous amounts of food, which supported an extraordinary diversity and size of animals. A casual observer of that world might have concluded that it was a perfect world, abundant, productive, balanced. But when the conditions that produced it changed, that entire extraordinary system was disrupted. The giant animals that depended on specific conditions found those conditions slowly removed from beneath them. The system that had been so rich and so balanced was not robust against change. It was robust within a specific range of conditions. Outside that range, it was as fragile as anything else. Our world today, with all its richness and diversity of life, is also calibrated to a specific range of conditions. The ecosystems we depend on, from the agricultural systems that feed us to the natural systems that provide clean water and clean air and stable climate patterns, are calibrated to conditions that have been relatively stable for thousands of years. The animals and plants in those systems have adapted to those conditions over many generations. When those conditions change, the disruption is not simply a matter of it getting warmer. It is a matter of every species in every ecosystem facing simultaneously a world it was not designed for. Some will adapt, some will not. Some will expand their ranges in ways that create new competitions and new disruptions elsewhere. The net effect is not simply a warmer world, but a reshuffled world, a world in which the relationships between species, between predator and prey, between plant and pollinator, between parasite and host, are all thrown into uncertainty at once. Titanoboa is a beautiful example of what the deep past can teach us about the future. It is not a warning that sounds like an alarm. It is a warning that sounds like a story, a quiet, long, patient story told in the language of stone, about a world that was extraordinary while it lasted, about an animal that was perfectly suited to it, and about what happens when the world and the animal are no longer aligned. The scientists who found Titanoboa, Jonathan Bloch and Carlos Jaramillo, and the Colombian researchers and the mine workers who made it possible, did something that goes beyond finding a remarkable fossil. They found a window into a world that was entirely different from ours and yet operated by exactly the same rules. They found a confirmation that the biology and the physics and the climate science that we study today are the same biology and physics and climate science that have governed this planet for hundreds of millions of years. And the window shows us something we need to see. It shows us that this planet has capabilities we have not seen in our own lifetimes, capabilities it can deploy again under the right conditions. Not exactly, not a rerun. History does not work that way, but variations on themes, echoes of possibilities that the bones in the ground have recorded and preserved and offered to us if we are willing to read them. In a mine in Colombia, the ground is still yielding its secrets. More fossils are being found every year at Cerrillon. More fragments are being pulled from the ancient rock and cleaned and measured and added to our growing picture of this lost world. Scientists who are working there today believe the full story of the Cerrillon ecosystem has not yet been told. There may be more species. There may be better preserved Titanoboa specimens. There may be a skull, which has never been found, and which would tell us extraordinary things about the animal's sensory anatomy. There may be evidence of nesting behavior, of feeding, of interaction between species, preserved in positions and associations that tell stories the individual bones cannot tell alone. The Cerrillon Formation is not a closed book, it is an open one, and the pages are still being turned. And so we come back to the beginning, to darkness, to a slow, deep sound in the darkness, to the breathing of something enormous and patient and ancient. It is 60 million years ago. Somewhere in a warm, flat, wet, impossibly fertile tropical world, a very long, dark shape settles into the shallow water of a slow river. It spreads itself across the soft mud of the bottom, with a stillness so complete that the water flows over it without a ripple, without any sign that something enormous lies just beneath the surface. The temperature of the water is around 32 degrees Celsius. The forest on both banks is a dense wall of green. Somewhere above the canopy, the sun is moving through a humid sky. Insects make sounds in the ferns. A large turtle moves slowly through the shallows 50 meters upstream. The river carries the faint scent of fish. Titanoboa waits. It does not know what it is. It carries no awareness of its own significance. It has no knowledge of the extraordinary biological machine it is. It does not know that it is the largest snake that has ever lived or that it will ever live. It does not know that the warmth it absorbs from the water around it is the warmth of a planetary system operating at its most extreme. It does not know that 60 million years from now, in a world it cannot imagine, a creature with no scales and no coils will dig its bones out of a seam of ancient rock and spend years trying to understand what it had been. It only knows the warmth pressing against its coils, the slow chemical conversation the river is having with its tongue, the patient accumulation of information from the world around it, building toward the one moment that matters. And it waits. Titanoboa cerrillonensis, 13 meters of muscle, bone, and scale, the son of the Paleocene, the largest predator its world had ever known, dead for 58 million years, and still, in the quiet patience of its resting image, still trying to tell us something about warmth, about time, about what this planet is capable of, and what it costs when the conditions that make extraordinary things possible finally and quietly go away. We found you in the rock, we read your story in your bones, and we will carry it with us. Rest now. The river is still warm.